Now, these ideas or results that I will present are motivated by my co-authors, and it is the result of a quite long thought process. And my work recently has been supported kindly by Mark Fleury, who's also on this call. Now, specifically, what I will be focusing on is to understand which type of electromagnetic wave is present in Zitterbewegung, and how to even understand longitudinal electromagnetic waves, because that's not something we find in standard textbooks. And also I will address hydrodynamic analogy. But so what I will start with is the context. The context is the evolution of fundamental forces perception. And there are two themes shown on the left and the right, which will be converging. So on the left, the main event that is very important from our point of view is Einstein's insight that we can think of gravity not as a force, but as a manifestation of space-time curvature. So that means that when Earth is going around the sun, Earth really thinks it's flying in a straight line in local space-time, but globally the space-time is curved, so the local straight motion is actually a curved motion when looking from far away. And this naturally leads to the question, can electromagnetic interactions also be written in terms of space-time curvature? Einstein thought long about this question, but he did not get any useful results. Then shortly after him, Hermann Weyl also formulated an attempted formulation of writing electromagnetism in terms of space-time curvature, but this was also not successful. And there were a number of others. I would like to highlight here a most recent attempt, which in my opinion is the best attempt. It's by Finnish scientist Jussi Lindgren, and Jussi has succeeded, in my opinion, to write Maxwell equation in terms of space-time curvature, and he shows that electric and magnetic forces can also be thought as manifestations of space-time curvature. And in course of doing so, he realized that the only way this can be achieved is to formulate electric charges also as a manifestation of space-time curvature. You cannot just look at forces and charges separately, but you actually have to address the difficult question of how to formulate electric charges as well in this geometric framework. So the result is this article, Electromagnetism as Purely Geometric Theory, and it will be soon published in Journal of Physics. So the other thread on the right concerns Maxwell equation itself. So Maxwell equation is a differential equation of the vector potential field plus electric charges. In essence, electric charges are put into it by hand, so it doesn't answer the question of what the charges themselves made of. And if one wants to formulate a theory, a field theory, then a natural question is to ask, can we formulate Maxwell equation purely in terms of electromagnetic fields? Can it be written as a pure field theory? And there has been a few attempts at that at the middle of 20th century. And here I'm highlighting the most recent attempt, which again, in my opinion, is the most successful attempt accomplished by Giorgio Vassallo. So he writes Maxwell equation as a purely field equation. This is also the simplest formulation of Maxwell equation, and it's a gaugeless electromagnetic field equation. So his results are published in this article, Maxwell's equation and Occam's razor, that was published already in 2017. Now, I did look at both of these articles and look the correspondence. And what is interesting is that they really show the same physics and the same picture. So it's two different type of approaches, but they converge to the same point, and they are just two aspects of the same model. And I thought that's very interesting that two very different approaches and thoughts finally lead to the same physics. So I encourage everyone to read these two articles. And in the following part of my talk, I will take these two references as the starting point, and I will be calculating starting from these. Now, here comes the question of hydrodynamics analogy, which was mentioned by Jarek before. And in this slide, I'm showing a table that's compiled by Olivier Roussel, who's also on this call today, that shows how we can look at the analogy between various quantities and measures from fluid dynamics and from electromagnetism. And what you can see is that in fluid dynamics, we are concerned with calculating and modeling fluid velocity. And if we want to have the equivalent picture on electrodynamics, then we have to consider the vector potential A as some kind of motion or speed that is equivalent to the fluid velocity. So the analogy starts from this equivalence, and then you can see that for almost every hydrodynamic quantity, we can find a very analogous electromagnetic quantity. Now, this is very nice so far, but when we think of the waves, then this leads to a problem, because in fluid dynamics, we have longitudinal waves, but in electromagnetism, we see only transversal waves, right? That's what we find in the textbooks when we look at what light waves or what radio waves we have. And then that's surprising, because given all these analogies, why would the waves be so completely different? Also, if you look at the Coulomb gauge condition that is often used in electrodynamic calculations, you can find that it corresponds to the fluid incompressibility condition. And by applying a fluid incompressibility condition, you are eliminating any possibility of longitudinal wave, because longitudinal wave presupposes a compressibility. So this somehow indicates that by applying gauges to electromagnetic theory, we are cutting out part of the solution, and so maybe we are losing one part of the theory which describes longitudinal waves. So we have to look at the formulation of electromagnetic theory that encompasses the full picture and allows both longitudinal and transversal waves. So this kind of formulation is given by the gaugeless electromagnetic theory of Giorgio Vassallo that is described in reference 2 that I mentioned. And to get the dynamics of waves, we have to start from the Lagrangian formulation, and the Lagrangian will give then all the dynamics of the field evolution. And here on the left, you can see Giorgio's formulation for the Lagrangian of the electromagnetic field. And I contrast it to the standard model Lagrangian of the electroweak theory. And so this thing on the right is a monstrosity. And the only reason I show it is just to convey that when you hear people talking about standard model electroweak theory, it's really this type of monster Lagrangian that they have in mind to work with. Okay, but our focus will be to understand the Lagrangian on the left. So what you see is that it's a very simple expression of the um, electromagnetic vector potential. So you take the vector potential and you apply the space-time derivative. That's this sigma operator. Now, this application of the space-time derivative is done under space-time algebra. So that's the geometric algebra of our space-time. And this multiplication is the corresponding Clifford multiplication. But essentially, this gives you the electromagnetic fields in this geometric algebra. And the Lagrangian expression itself is just the norm square of the fields, right? So it's a very simple conceptually that your electromagnetic Lagrangian is nothing else but the squared amplitude of the electromagnetic fields. And sometimes I ask the question why I write this with Clifford algebra, why I don't use normal Euclidean operators. Well, it's possible to make it more complicated, but I do not want to make it more complicated because space-time has a geometric structure that's different from the Euclidean geometry, and in order to see that geometry clearly, we should use, in my opinion, the corresponding geometric algebra. Otherwise, we have a risk of getting lost in the notation, whereas here the notation is very clear. All right, so this is the Lagrangian we're going to be studying. And I think everybody in the audience is familiar with Lagrangian mechanics. In any case, I have two references here at the bottom of the screen that may be useful, that are probably useful to highlight the importance of Lagrangian approach when studying electromagnetic waves and quantum mechanical waves. I personally learned Lagrangian mechanics in the context of mechanics bodies, and it was in my education not as much emphasized how crucial it is to understand the motion and properties of waves. So that's why I saw that these videos that I have here, they are very nice introduction to show you why the Lagrangian approach is a very useful and powerful formalism to understand the dynamics of the electromagnetic waves. All right, so now let's go ahead and unpack this Lagrangian in terms of electromagnetic fields. So this algebra that you see here is just unpacking this space-time derivative of the vector potential in terms of the electric field, magnetic field, and scalar field. So normally we see only electric and magnetic fields when we work with electromagnetism, and in the traditional approach to electromagnetism, the role of the applied gauges is to eliminate scalar fields. But here we work with a gaugeless theory, and we want to look at all the components of the fields. We do not want to eliminate anything. And the interesting thing when you look at this Lagrangian in terms of written in terms of fields is that it has two components circled by this red and blue ellipses. The red ellipse is the Lagrangian of the transversal electromagnetic fields. So this part in the left, it's 0 for a uniform transversal wave. So what that means is that the electric and magnetic fields induce each other in such a way that this overall expression remains 0. And when you look at the right side, it is really clear, it is shouting at you that this is a longitudinal wave expression. The electric and magnetic fields are parallel. And so this right side, that is a new result from Giorgio Vassallo's approach, is the longitudinal waves Lagrangian component, right? So as before, this longitudinal Lagrangian is also zero for a uniform electromagnetic wave. So what it means is that the electromagnetic scalar field and the electric and magnetic field, they induce each other in such a way that the overall Lagrangian remains zero. And both of these components are Lorentz invariant as expected. So now this is a very nice result that we got a Lagrangian expression that is decomposing into longitudinal and transversal parts. And let's look into the longitudinal part in a bit different light. So what we can do with some algebraic manipulation is to rewrite this longitudinal part into a different form, the current density times the vector potential. And this calculation I do not prove here because it's a bit tedious, but you can find it in the reference to the details if you want to check. So just applying some algebra and Maxwell equation, you can convert this form on the left into J dot A on the right, and both of these are 4 vectors. So now the interesting thing is that this J dot A is actually a well-known term in electromagnetism. It's called the interaction term of the electromagnetic Lagrangian density. So when people talk of the electromagnetic Lagrangian, similarly to what was presented to Jarek, then there are 2 parts. The first part is the field term that is describing the electromagnetic wave propagation, and the second part is called the interaction term. This J times A is describing the interaction of electromagnetic fields and charges. So this part is well known, but what is not well known before is that this interaction term is actually a longitudinal wave. And that is really what I want to emphasize here, because when we just start with the ordinary Maxwell equation and we have the current density part, well, we really don't know what that current is made of, what it really means geometrically. But with Giorgio Vassallo's approach, it's possible to identify that this interaction term, the J dot A, is really a longitudinal electromagnetic wave. And that is very important, as we'll see. So to see the significance of this result, let us apply it to the Electron Zitterbewegung. And here I have a cross-section of the electron's particle aspect. Now the electron dimensions are measured experimentally, right? So we have the classical electron radius that's measured by scattering experiments, 2.82 femtometers. And then this gives one radius of the electron, and the other radius is the reduced Compton radius. So this is 386 femtometers, and this Compton radius is defining the electron's Zitterbewegung radius, right? So the electron's Zitterbewegung radius is a Zitterbewegung current, and this Zitterbewegung current generates the electron spin, which has a well-defined magnetic moment value, right? And so up to now, the big question was, what is really that current? How to understand this current? Why is it stable? And now in the following slides, I will show you some consequences when we understand that this current that we see appearing here is a longitudinal electromagnetic wave. Once we realize that, let us see what the consequences are. So the first consequence that we can study what happens when we look at the electron from a different reference frame, that is when we do a Lorentz transformation. So this wave going around on the left, it represents this longitudinal wave of the Electron Zitterbewegung. And when we look at a wave from a boosted reference frame, then any wave is subject to the Doppler effect, right? So in this case, what we have to apply is the relativistic transversal Doppler effect. And this you can check when you do the calculation. This relativistic Doppler effect is shrinking by the gamma boost factor, the electron size along these x and y axes. Along the z-axis, we have the usual Lorentz contraction. So what this means is that when we are looking at the electron from a boosted reference frame and our boost factor is this gamma L, we see the electron size shrinking from by gamma L. And here you can see it pictorially that the electron Zitterbewegung, this dark blue, is in the rest frame, and then you can see how it looks like when we look at it from various reference frames. Now, why is this very important? It is important because we have a relativistic increase of the electron mass, and insofar as we consider electron mass to be electromagnetic field energy, then we have to explain why the electromagnetic field energy is increasing when we look at it from a boosted reference frame. And now you can see a very tangible physical meaning how it happens, that when the wave shrinks by the Doppler effect, the electric fields get more and more intense as you get closer to this shrunken size of the electron. So you can see a very tangible explanation that as the electron shrinks down, the electromagnetic field energy increases just as the fields get more intense at these shorter distances. So, I think this is an important geometric result because up to now it was really not clear why the relativistic electron mass should increase if the mass is comprising electromagnetic field energy. Okay, then the other consequence you can see when you look at the quantum mechanical waves. So let's consider again looking at the electron from a boosted reference frame, and the Lorentz boost is mixing the time components and the space components according to this matrix. And when you consider in the time component a wave oscillation with the frequency identified by de Broglie, then you can apply this Lorentz boost calculation, and by mixing the time component of this Zitterbewegung frequency into the space component, you can calculate what the corresponding wave number is. And so here I have this calculation. You can verify it. What you end up by following de Broglie hypothesis is that h bar times the wave number is exactly equal to the electron's momentum, kinetic momentum. So you can recognize that this is the basic postulate of quantum mechanics. However, in our case, it doesn't have to be a postulate. What we recognize here is that the appearing quantum mechanical wave is simply the Lorentz boosted component of the Zitterbewegung wave's time component, right? So when we talk about a quantum mechanical wave, all we are looking at is just the Lorentz transformed component of the Zitterbewegung wave. So the quantum mechanical phase is the Zitterbewegung phase, but for all of this to make sense, the Zitterbewegung itself has to be some kind of a wave. And well, this result was known before, and because of this result, many people were considering Zitterbewegung to be some kind of a enclosed photon. But if you are talking about a photon, then it's not clear where is the charge coming from, because photon has no charge. But now that you consider the Zitterbewegung being actually a longitudinal wave, as I showed in the previous slide, it does define the charge. So you have both the Zitterbewegung charge current and the quantum mechanical wave. Okay. So now let's move on to the next topic and investigate the radiation that is given off by the electron. So when the electron changes its kinetic energy, then it gives off transversal electromagnetic radiation during its acceleration. So this I again showed geometrically what it means when the electron's kinetic energy is changing. It is a change in perpendicular direction to its Zitterbewegung plane. So you can consider emission of a transversal wave to be happening when the electron is accelerating in perpendicular direction to its Zitterbewegung plane. Okay, but what happens if there is some change in the Zitterbewegung plane itself, not perpendicular direction, but in the Zitterbewegung plane? So in other words, if the Zitterbewegung current could be converted to an electromagnetic wave, what kind of radiation would it be? So this question is tied to the question that Zitterbewegung critics often say, namely that if there is a Zitterbewegung current going around, then it should involve some kind of acceleration of charges, and accelerating charges should radiate. So what kind of radiation it is? Why don't we see that radiation? Where is the Zitterbewegung radiation? Okay, so let's consider if the Zitterbewegung could radiate, what kind of radiation it would give off. And the best analogy, I think, or the best example to look at is the muon electron decay. So the muon is considered to be an energetic electron, at least as a first approximation. You can think of a muon as a heavy electron. Why can we think of it that way? Firstly, a muon is always decaying into an electron. So the only way for muon to decay is for its Zitterbewegung structure to be changing into electron Zitterbewegung structure. And secondly, the muon's magnetic moment, again to a first approximation, is just the mass-scaled version of the electron's magnetic moment. So this means that you give additional mass to the electron, you shrink down its Zitterbewegung current, and you end up with a particle that looks like a muon. And in case of a muon decay, that very, very tight muon Zitterbewegung, which has about 200 times smaller radius than electron Zitterbewegung, is gradually expanding until arriving at a stable position of being electron Zitterbewegung. So what is emitted during this decay? Well, experiments show that it's a neutrino wave that's being emitted. And as I showed in the preceding slides, insofar as we think of Zitterbewegung current as being a longitudinal electromagnetic wave, then it's quite logical that a radiative change of the longitudinal wave should give off some kind of a longitudinal electromagnetic radiation. So this suggests that neutrino could be nothing else but some kind of a trivial longitudinal wave solution to the Maxwell equation. And that is my opinion that to understand what neutrinos really are, we have to look for the trivial longitudinal solutions to Maxwell equation. So trivial meaning some kind of a plane wave solution. The electron is, as Jarek was explaining, is obviously not a trivial solution because electron has a topology and electron has a very specific mass and charge value that is required for its stabilization. But the neutrino just propagates at light speed, and there is no reason why that could not be a trivial solution to Maxwell equation. Okay, so this now addresses the question of what Zitterbewegung radiation would look like, but it of course does not answer the question of why the electron does not radiate away its mass. So there has to be something that stabilizes this topology of the electron, and that is a big challenge to understand the electron stability conditions. Okay, so if you are interested to study more about the longitudinal wave solutions, I can recommend the book written together with my co-authors, Unified Field Theory and Occam's Razor. Many of the ideas I presented today are in that book, and also there are some of these longitudinal wave solutions calculated explicitly. But also you can do it as a homework, starting from the Lagrangian I showed you a few slides ago. Actually, you should be able to just calculate yourself what would be the trivial wave solutions of this longitudinal part. Okay, so now these are concluding remarks. So before this conference, there were a number of questions that were posed. And the idea of today's presentations, as I understand, is to answer these basic questions about electron Zitterbewegung. So first question, when we look at the elementary particle as the electron, what is actually circulating in the Zitterbewegung current? And my proposition in this presentation was that we are seeing a longitudinal electromagnetic wave that circulates at light speed. And this longitudinal wave creates the electron spin angular momentum. Okay, so what propels this periodic process? It is electromagnetic induction. And why does it maintain a constant frequency? Why it does not radiate? Well, it is obvious from what I showed in the previous slides that this longitudinal wave has to minimize the Lagrangian action, but beyond that, beyond this trivial statement, there is still some further geometric or topological condition to the stability that we have to understand. So for example, Jarek's slides gave some ideas. Now, next question, it is often assumed that Zitterbewegung frequency is proportional to the mass. Is it true? And yes, in my opinion, Zitterbewegung frequency is proportional to the particle mass. And finally, does electron Zitterbewegung model apply to the proton? And again, the answer is yes. I have been studying this question, and I found that the proton can be described by analogous approach as the electron, but one important difference is that their Zitterbewegung topology is different. So that, in my view, electron-proton difference is just a Zitterbewegung topology difference.